Now as we look at the notes, we want to do a couple of applications with symmetry. The top box here, the types of symmetry summary, I walked through this on the previous video. So if you just need a quick refresher or need to see where all these graphs here come from, all this was done on the previous video. The important thing to realize with this is as we test for the polar axis symmetry, for every r theta, we're going to convert it to an r negative theta. I could use the second form, but the pi minus theta becomes a little more complex. Might as well just use r and negative theta. So for every r theta, we're going to substitute in r negative theta. When we have theta equals pi over 2, for every r theta, we're going to substitute in negative r negative theta. And then for symmetry around the pole, for every r theta, we're going to plug in negative r theta. Now a couple things that are different about polar than rectangular coordinates. And probably the first thing is that even though I can do a test for this symmetry, I can't necessarily prove it doesn't exist. So right here, if you'd highlight, note for these tests for summary, a positive result is conclusive, while a negative result is inconclusive for symmetry. What that's saying is if I do get a positive result, meaning my equation does equal my original when I'm done substituting in, I can say I have symmetry. But if I get a negative result, I can't necessarily say that I don't have it. I have to say it appears that I don't. And the reason for that is you know that there are multiple ways that you can write points in polar coordinates. And just with the whole infinite number of correct answers and infinite number of wrong answers for polar coordinate points, we can't necessarily eliminate the fact that we're looking at a different perspective of that same polar graph, or maybe something just wasn't covered in the equation. So we would use a graphical approach to confirm. So if we get a negative result from our algebra, which means my final equation does not equal the original equation, I can only say it's most likely the case that it's not going to have that type of symmetry. As a quick review, how these graphs look in polar coordinates, r equals sine theta is a circle around the theta equals pi over 2 line, or you know it as the y-axis. R equals the cosine of theta is a circle that's reflected around the x-axis. And those are the types of symmetry. We've got the polar axis symmetry here, the x-axis, and theta equals pi over 2, the y-axis. Now this point here, how do the graphs of 5 plus cosine of theta and r equals negative 5 plus cosine of theta differ? You might say those are completely different equations, and you're right, they do look completely different. But there's only one thing that's different, and it's the 5 and the negative 5 in front. This right here, this cosine of theta, that's the function, and those are identical. The negative 5 here versus the positive 5, that's being added or subtracted after you find the trig function. So the net result of that is if we graph it, we're going to see we have the identical graph, but just each of the points are going to be written in an alternate polar form. But the overall picture is identical. And if you can recognize this pattern that if I have the exact same function and everything's identical with the exception of one sign, and in this case the a piece, then I can say the graphs are identical. If you don't believe me on that, we can do a quick verification on the graphing calculator. I've put in the equation 5 plus cosine of theta and negative 5 plus cosine of theta. And my second one I'm going to draw with a thicker black line just so you can see the difference. Now when I hit graph, the graph is going to start to be drawn, and I can hit the enter key to pause the graph as it's being drawn. So that's what I'm going to do. So I'm going to hit graph and then hit pause just for a moment. Notice this graph right here started out here and is going in the counterclockwise direction. I'll continue along here and I'll pause it again. And in a moment the graph is going to complete at that point. You're then going to see the second graph drawn on top of this in a thicker line. So remember, this graph started over here in the positive x-axis area. So I'm going to unpause, and I'm going to pause it and unpause again. And you can see the thicker black line starting to be drawn from over here. And right now it's paused, so it's right there. But if I unpause it, you're going to see the line continue. There it goes all the way around back to the end. So the difference with that negative sign on that A piece is I get the exact same shape, but I just have a different starting and ending point, provided that I graph the entire picture. And that's one of the key pieces of solving these equations, that even though these two graphs do look different, they are identical when you look at the big picture. The only difference is a different starting and ending point, and each of these points, if I were to list out the polar form, is a different polar point, but I could always convert them to be identical. So now what we'd like to do is we'd like to do a test for symmetry. And for this, we're going to test all three. R equals 2 minus sine theta. Now before I do anything, I know that the sine graph is reflected around theta equals pi over 2. So my first gut instinct is going to be, I'm going to think this is going to be tied to that theta equals pi over 2. But I need to just confirm that. So let's do the test for all three. The polar axis. For every r theta, we're going to convert that to r negative theta. So r equals 2 minus the sine of theta. We'll plug in a negative theta, so we're going to convert everything to r negative theta. And here we're looking at the even and odd identities. Sine is an odd function, so the negative sign comes out in front. And since we already have a negative there, it's going to become positive. So r equals 2 plus the sine of theta. So what I do is I look at my original and I look at my final. And I ask, are they the same? And the answer is no. So it would appear that this does not have polar axis symmetry. I can't eliminate it for sure, but most likely I don't. The second one, theta equals pi over 2. For that one, for every r theta, we're going to plug in negative r, negative theta. So my original, r equals 2 minus the sine of theta. I'm going to plug in a negative r. And then I'm going to get r by itself. So we'll first, once again, apply that even and odd identity. Sine is odd, so the negative sign comes out. And then we'll divide everything through by a negative. So what I'm comparing right now are these two equations. And are they the same? And the answer is yes, these are the same. This is the idea that we had right here. I've got the same negative sine function there, and the only part that's different is the sign of the a value in this case. So these two graphs are the same, and if I were to graph them on the graphing calculator, the only difference is that they'd have a different starting point and a different ending point when I look at it from the graph's perspective. So this one, yes, we definitely do have theta equals pi over 2 symmetry. The final one we're going to check is the pole. And for the pole, for every r theta, we're going to convert that to negative r theta. So my original, r equals 2 minus the sine of theta. We'll plug in a negative r and positive theta. And when I solve that, r equals negative 2 plus the sine of theta. I can make the comparison here, and I can see, are they the same? And no, they aren't the same. So this one most likely does not have polar symmetry. If I plug it into my graphing calculator, I can confirm these definitely don't have a polar axis symmetry or a pole symmetry. It only has theta equals pi over 2. But once again, algebraically, we can't definitively rule them out. We can just say most likely they don't have those types of symmetry.